Hey everybody, thanks for coming to my talk. Super exciting to see people responding to some hard work, and I think it's interesting as well by its own. And I want to thank as well Black Hat for having me, despite the cute name that I gave the talk. And let's get onto it. So, my name is Menscher. I'm a software researcher from Israel. For my day job, I like to take on challenges that involve a lot of reverse engineering, be it OS, kernels, firmwares, you name it. And I grew a special enthusiasm with vulnerability. I've been doing vulnerabilities a long time now, and I grew an appreciation for exotic bugs, and I have the special privilege today to tell you about such an exotic bug that I've found recently in the Windows fragmentation mechanism. And the reason I think it's interesting, well, one reason is it's quite a simple bug, really. It's quite even a stupid mistake. And nonetheless, it has a really significant impact on the security of the system. And you'll see it's quite the opposite than the intention of the designers had been. And another reason is, well, it really is a simple bug. It has been on the surface of a driver like TCP/IP/sys, TCP/IP/sys, and which is something that I'd considered picked clean before, and not the best target for reverse engineering and vulnerability hunting. And this bug, which really should have been found using automated tools in the security design lifecycle that they have, has existed for the past 5.5 years. And this makes me think that there are other such bugs lurking, simple bugs, and I'd encourage you really to explore such, pillars of Windows as TCP/IP/sys, and you will find such bugs, and therefore it's worthwhile to, I think, relearn maybe the fragmentation and such things that that are relics of the past, maybe in attacks, and some of them have been brought back to life now. But let's quickly recap fragmentation, and fragmentation is really when I'm sending a packet that's too large for the underlying link layer, and in this situation what happens is any router in the middle, and also myself as the sender, we are allowed to split this packet into small fragments, and in this case, so that we can reconstruct it, the other side can reconstruct it, we assign all the fragments that belong to the same packet. We assign them the same identification. Identification is a field on the fragment. We assign the same IP, or we also call it IP ID. We assign the same IP ID to all the fragments that belong to the same packet. There's also a notion of offsets within the packet, and a flag that tells us whether or more there are more fragments coming up, or this is the end of the packet. Another thing is that the fragments that are not yet completed to a whole packet are stored in a cache of the reassembling part. And the last fact about fragmentation is that it's undeniably cursed, and we've known that for a long time, actually, from at least '87. And what these guys mean is that that there's an implicit trust between the reassembling part and the sender, in that the sender wouldn't bombard them with fragments, blowing up the resources, the caches, and creating a denial of service. And this is not the final denial of service, the last denial of service to be found in fragmentation. Later there has been, for example, blacked out on the name of the vulnerability, but there have been vulnerabilities in the implementations, widely affecting vulnerabilities, but in the modern times they're less and less. But I'm gonna reference another denial of service vulnerability in fragmentation itself. But I think there are more interesting things to be found with the fragmentation. One of them is it has been found as a great way to evade IDSs, and the way you do it is you'd send multiple fragments, overlapping fragments. This is one way to do it, and the fragments, the IDS wouldn't know which of the fragments to discard in case, unless it has really adequately implemented the same exact checks as the receiver would, and you'd create an IDS evasion. And it's even been implemented as a router that you send your packets through to the sender to do it. And this is one example. Another example has been suggested by Kaminsky in 2005, where you play with cache times that are different between the IDS and the actual receiver or the router. Again, creating an IDS evasion. But I think a more interesting, or maybe the more interesting attacks have been revolving around the fact that operating systems at the time have implemented the algorithm to generate the IP IDs very naively in the form of a global counter, actually. Right up until modern times, 2012, 2011 in different operating systems. And hackers have found creative ways, creative things to do with it. For example, to count hosts behind a NAT. The other example is to scan the network really stealthily without exposing the IP address of the compromised host throughout the network. But the more interesting even attack has been suggested by Zalewski in 2003. And he was researching ways to inject packets into TCP sessions where you have to guess, predict the TCP sequence or the destination port that you have, which are hard to guess. And you realize, well, if there's such a mechanism that, already has this, the first fragment of the packet would have these data valid. We don't have to guess it. You only have to guess the IP ID of the packet, and definitely when it's implemented as a global counter, then it's a cool thing because you can inject data into the session. The downside of this attack is that you'd create invalid checksum. But we do know that some network gear would either pass it, ignore it, pass it as if it's okay, or even fix it for you in some other cases. But a cooler attack even, I think, has been suggested later based on this work by Gilad and Herzberg in 2011. And they found that in a case of a NAT, and this also applies to the case of you have a tunneled network, then the NAT what it would do is it would choose where to send your packet based on the data that's in the header that's the destination port. And so they figured if you decide to inject to the first fragment and not the following fragments, and maybe the following fragments have data that you're really interested in, then you can effectively create, you can intercept those fragments, the data, if you have a host behind the NAT, because you'd get the NAT to route the packets to you. And they've also found that this is a really effective denial of service attack. They claim to have dropped 40% of fragmented network, fragmented traffic in their network. And yeah, so obviously the vendors have rushed in to close this issue. Obviously not. Only in 2012 with Windows 8, Windows have moved implementation, Linux around that time as well, where they now create you'd get an IP ID differently depending on the IP path, and this is their jargon, and we're going to use it. And by IP path I mean, and they mean, it's the pair of the source and destination IP addresses. And so effectively, what you have, an attacker couldn't guess any IP ID series other than his own conversation. And so everyone was happy and safe as long as you don't touch that code. But obviously for 8.1, a year later, and actually someone from Microsoft told me informally that, oh, this is such a classic bug, you don't have to understand the details yet, but this is such a classic bug. We had a refactor, and you just changed an array to a pointer, and then the size of it came fine. So I was curious, what's this refactor? And I opened up the disassembly, but seriously, I hadn't found anything different other than the bug being introduced, and another thing that could be just a compiler change. So anyway, let's dive into how the IP-ID is generated in order to understand the attacks and the implications. in the new form. So it's all about IP path. And IP path, I remind you, is the source and destination IP addresses. And you build the identification field with connecting something called base and an increment. And the base is simply just random 4 bytes, a random D word, initializes boot, XOR the hash of the IP path. And you add to that a random number out of a table of random numbers. You pick a cell by, again, the hash of the IP path. And so the second part should give you that sweet separation between conversations that you have on IP path, this randomity between conversations. So this actually to me looked really good, and until you look at the way it's initialized. So what happens is they have to initialize the random table, and the way they do it is they allocate. You don't have to understand really the graph. I'm explaining it. They allocate the dynamic memory for this table. It's 8,000 hex bytes, and the second thing they do is now they need to initialize it. And apparently they have been initializing it wrong, initializing only 8 bytes effectively out of the table. And the rest of it gets worse for them, is previously used kernel memory that the user shouldn't be able to see, because it will help him bypass KSLR, and definitely not a random host in the network, unauthenticated or nothing. And it gets better for us. So statistically, what happens is, because you get multiple pages, a lot of the pages are practically 0. You get many, many zeros, and you have the increment that you get in the end as a 0. And this is great for us because given enough samples, it's really for a significant number of samples, you get this true, that the identification exactly equals the base. And let's talk a little bit about this base, now that we know that the identification is just that for many samples. The base is 4 random bytes, XOR a hash of the IP path, and let's explore the hash. Well, the hash is something that I don't expect most of you to know if you're coming from security, because it's something that, well, I didn't know it either. It's something that comes from performance, and it's called a Toeplitz hash. And quick history lesson, well, Microsoft has been, the reason it's there is Microsoft has been implementing something called RSS, that's a receive side scaling. And what they're doing is, what RSS does is they're distributing the load that it takes to process packets evenly between processors. And the way they do it is they hash some part of the packet with this hash, and then they use the hash to assign uniformly a processor. But that doesn't account for why we're doing it on the sending side, as if it's receive side scaling, and B, more importantly, is that doesn't account for why they're using it in a security critical thing such as the IP ID generation. You gotta ask Microsoft for that. But what I do know is how it works. I'm going to explain it to you. So you start off with a key, and the key is 40 bytes long. Initialized again at boot, 40 bytes long of key. And they take now windows out of that key, windows of 4 bytes. And with those 4 bytes, and I'll explain it exactly later, but what you got to know is using the 4-byte windows, they create matrices, a 4x4 matrix that is something out of the key, and I'll explain that something later. And from each window, 1 matrix. And we use those matrices against the input to create the hash. What we do is we take the input nibble by nibble, and each nibble is an index to simply an index. If it's 2, then we take cell number 2. If it's F, we take cell number F, the 15th cell. And the final result of the hash is the XOR of all the values of all the matrices as indexed by the input. And this gives us some cool characteristics, which I'll give the bottom line of in a second. I'm explaining the way that our matrices are built, and each matrix is built with a different number of different roles, a roll of different amount to the key. So you have a roll of 0 on the 8th cell that's marked there. You have two elements joined together by XOR, for example, the cell to its right, a roll of 3 and a roll of 0 XOR together. And actually, if you've seen the cell number 8, which is exactly the key part, because it's a roll of 0 to the key part, then actually this phenomena is true for all two pairs, all two cells that have that their indices are XOR of 8 of each other. So well, and this is an example. Cell a roll of 2 XOR a roll of 2 XOR 0 gives again the key part exactly. It's true for all the pairs of cells that have XOR of 8 of their indices. So together with the fact that this has been all along just XOR arithmetics on the base side, we can see that given two inputs of that hash, and we're talking about the hash, and again the inputs for that hash is just two IP addresses. That's, for example, I'm sending from 10.0.0.1 to 10.0.0.2. Well, for identical inputs that only differ by one nibble, and that nibble is XOR of 8 of each other, you'd get identical elements up until one element, which is the XOR of which would give you the key part again. And if we remind ourselves that the ID is that hash XOR something, and it's the same something for all IP IDs, then if you XOR two samples of those IP IDs where you have the increment as 0, then you'd actually get just out the key part. So imagine that you take two samples, you XOR them. There would be mostly the key parts statistically, and this is crazy. This is exactly the opposite of what I think they meant, the separation between the conversation. We have now a strong connection between IDs and the key, and this gives us attack number 1, which is key recovery. And the way you do it practically is you generate as many samples as you can of pairs of IP paths, of IP IDs that belong to IP paths organized with that XOR of 8, one nibble difference with them. Then you XOR those pairs, the values of the IP IDs, and you'd get key candidates. You can rank those key candidates and get the exact key out. Then you repeat it for the rest of the key parts. But I didn't tell you what good is it for to get that key out. But if you look closely at this weird connection that we have, then we know an identification where the increment of 0 exists because it helped us find the key. It was one of those that were correct with the key. We know the key part, and we can now start predicting IP IDs for different IP paths. So this leads us to attack number 2. It's quite complicated, I'll explain, to read kernel memory. And the reason it works is because you can predict the IP ID that comes out, and if you can actually get a sample of the IP ID that comes out, then what happens is the difference has to be the content of the table not being 0. The content of the table is the uninitialized kernel memory. And you can now read up to 8,000 hex of that uninitialized memory. And let's see a demo of it. All right. And this is sped up. What happens in the demo is we get many samples of these are key candidates, and we're ranking them because we've generated many pairs of IP paths that's given us different IP IDs. We have found a key that's outstanding in the ranks, and we've just started to get out some data, kernel data, and we're looking them up on the TCP IP sys memory. We found them, but not spot on, with an offset of 2, with an offset of 1. There's some reasons why it happens. I'm pretty sure that it's enough to bypass ASLR, but I think there's statistic ways to eliminate it, just to get it spot on, but I didn't go as far. going back to the presentation. So this was attack number 2, getting uninitialized kernel memory, and but I didn't. This doesn't connect to the attacks that I've mentioned previously. And the way it does is when you have we've implicitly just now predicted IP IDs for IP paths that are not our own, and this is actually practical for any IP path that doesn't have an increment of 0 to it, that does have an increment of 0 to it, and there are many of them. Actually, it's a zero-sum game. The more 0 increment that you have, the more IP IDs that you can guess, and the less 0 increments that you have, you can predict more IP IDs accurately. But for all those that have an increment of 0, it's a huge number. The problem is reduced to assessing the number of packets on the IP path. You can either guess because there's some cache time to the reassembling equipment, or with a side channel attack that you might have. And so this is the end. This brings up well, some of the attacks that I've mentioned previously, definitely the Zalewski attack, where you can inject data, and the interception attack that was suggested by Gilad and Herzberg. And to sum up, I have a few takeaways that I want to share. The first is actually to reiterate every article that I've mentioned in here, mentioned this research. They're stating boldly, do anything you can to not fragment in your network. And the second one is my own thoughts, that you should never refactor working code. It's not worth it. And the third piece would be my advice to you. Go out on your search, such pillars of Windows, things that are considered picked clean, such as TCP/IP, sys, and you will find it. You'll find it before automated tools, if this is an example. And thank you. Yeah, that's all I have. If you have questions, this is the time. We're also easily found in on mail, Twitter. That's it. Thanks. Thank you, guys. All right, this is the time for questions. Really a quick one, because we have 2 minutes. If someone, I can't see, but if someone's raising his hand, I don't see, but maybe you can see if someone's raising his hand. Oh, there's a guy.
Thanks. Has this been patched, and what's the timeline on that?
All right, it has been patched on not the November patch Tuesday, but the October one. So it's quite recent, and therefore I think it's worthwhile to experiment with it, with those attacks. Definitely going to see it in the next few months on production networks. And the timeline has been 4 months until they have disclosed it, and until they have patched it after my disclosure. And that answers?
Yeah, thanks.
All right. So I think we have a time for just a quick one, if anyone. All right, you can catch me in the hallway. Thank you. All right, thank you so much.